Are you just going straight to the table?
Rolling, yeah. We don't want it to fall again.
Okay, that would be bad.
Yeah.
Okay. So the final tomorrow, okay, it's going to be kind of like most tests. We only had two really big tests. And that's going to be mostly multiple choice with basically two big free response questions. One free response question is going to be on like the redox process, like a galvanic cell. Remember, there's two broad types of cells. You have galvanic or electrolytic. Those are the ones that occur spontaneously. And then you have, voltaic and galvanic mean the same thing. Electrolytic are the ones where you have to have the electricity, and that's where you have the non-spontaneous reactions. There's going to be a big problem on weak acid or strong acid in a titration. Okay, you know that's going to happen. So, because those are the two big topics that we have covered so far. Now, there's also going to be a smattering of kind of general knowledge stuff. Let's say, for example, I give you this problem. Let's just say you are given a sample of, let me see. No, it's just, you don't know what it is. It's just MCl. You don't know what the M is.
What about
That's
X?
the whole point.
XCl.
We could do X. You want to do X?
I want to do X. I want to do X.
Why is that in the other?
XCl. Better?
Yeah.
Okay. Okay. So since you all like X more than M, we'll go with X. So you have a sample, all you know is that it is a chloride, okay? Now, but since this is just XCl, what do you know about the oxidation state of X?
+1.
Why?
Because chlorine is -1.
Yeah, so it's a 1-to-1 ratio. So whatever X is has to have a charge of 1+. So right away, it can't be magnesium, it can't be calcium, it can't be iron 2, okay? So it's probably going to be something in group 1 or something that has an oxidation state of +1. It could be copper, for example. You could have copper 1 chloride. You could have silver chloride. You could have any number of ones that have a charge of 1+, but you know it has to have a charge of 1+. But the problem is I don't know what X is, okay? So, but I know how much mass of that I have. So I'm going to dissolve it in water. So right away I know that this thing is soluble, okay? Now, if something's soluble, what do you know about, would you worry about the Ksp as something that's soluble in water? No, why not, Jason?
Because it would be like so high because the forward reaction is really high.
Beautiful, okay? You only worry about Ksp values when they're really, really small, okay? So I'm going to dissolve this thing in 200 milliliters of water, okay? Then I'm going to add silver nitrate and it's going to form a precipitate. So what's going to be the precipitate that's going to form?
Silver chloride.
Okay, so here's what's going to be important. Because all chlorides are soluble except for silver, lead, and mercury, okay? So you know you're going to make a precipitate of silver chloride. So that's kind of the cool thing about this. So look at this in terms of your reaction. So you have XCl, plus silver nitrate, okay? So what are you gonna get out of this thing?
X nitrate plus.
X nitrate.
silver chloride.
And, so that's fine. What's your superhero name? Superhero name, I'm X nitrate. And AgCl. So here's what's gonna be important. Everything here is in a 1-to-1 ratio, okay? So if I can figure out how many moles of anything that I have, guess what? Then that mole to mole conversion is also just gonna be in a 1-to-1 ratio, okay? So if I know, if I've got 0.5 moles of silver chloride, that means that that's gonna produce 0.5 moles of silver nitrate, okay? Not necessarily, it won't be a 1-to-1 ratio of mass, but it'll be 1-to-1 ratio of moles, okay? So if I got 0.5 moles of silver chloride, I have to react that with 0.5 moles of silver nitrate. Okay, so that's gonna be an important part of the story. So, even though I don't tell you this, precipitate is dried, and that's 2.87 grams of what?
Of
Silver chloride.
Yeah, so again, you have to look at this in a sequence. So you're gonna add this stuff together, the silver chloride's gonna form, you're gonna pour this through some filtered paper, right? And that stuff is going to collect because the silver chloride is insoluble. So what's going to end up in the solution down below?
Silver
X.
chloride is a precipitate.
X
Silver
nitrate.
chloride is the precipitate, so what's going to end up?
X nitrate.
X nitrate, so I'm going to have X ions and I'm going to have
Nitrate ion.
nitrate ions, okay? Now, why don't I have to worry about them forming a precipitate?
Nitrate, man.
All nitrates are
Solid.
soluble. So are you going to alter the concentration of the nitrate ions? No, they're going to remain the same. Okay. So, I got 2.87 grams of ACL. So what can I do with that?
Turn that into moles
Of,
of silver chloride.
okay?
And then turn that into X chloride.
So I got
what do you say?
2.87 grams of
Use that to find the molar mass.
silver chloride, right?
Subtract out the chloride and you find X. Sorry, I'm getting ahead.
I appreciate the enthusiasm, Connor. I mean, don't get me wrong. So, somebody give me the molar mass of silver chloride.
Working on that right now.
It's 107 point something plus 35.5.
143.32.
143.3, and that's grams technically per mole, 1 mole, right? So if I do this conversion, what do I get?
Silver chloride.
Moles of,
Silver chloride.
so somebody take 2.87 and divide it by 143.3.
0.02.
Okay? Moles of silver chloride. So what else does that mean?
There's 0.02 moles of X chloride.
Okay? Because it's a 1-to-1 ratio. 1 mole, right? So that also means I've got 0.020 moles of X chloride. So now what?
Are you using X nitrate or chloride?
Same.
That's gonna be, yeah. In this case, what I'm trying to figure out, my XCl.
Oh, okay.
I could put anything up there, but what I'm trying to figure out is the fact that I'm trying to figure out my moles of XCl. Okay?
Use that to find
Now
the molar
what?
mass. Find the molar mass.
How?
Well,
Because the molar mass, here's what you have to understand. What are the units for molar mass?
Moles
Grams
over
per mole.
grams. Grams over moles.
Grams per mole, right? So molar mass of carbon is 12. That means you have 12 grams per mole of carbon.
Right.
Okay? Chlorine, 35.5. You have 35.5 grams per mole. So this is just the number of moles. So how can I find the molar mass?
Divide 0.82 by 0.02.
Yeah, because you're told that you had 0.85 grams of XCl. Okay? So if I know that mass, and I divide that by the moles, I can get my
Molar mass.
molar mass. So in this case, I'm going to take 0.02 moles and divide that by, or 0.85. So I'm going to take 0.85 grams of XCl and divide that by moles of XCl, and what do you get?
42.5.
And you get 42.5 grams per mole. Well, chlorine is
That is 35.45 grams.
35.5.
Yeah.
Okay? So I know if I get this answer, and it's less than 35.5 grams per mole, I've done something horribly wrong. Okay, because at a minimum, I've got to have 35.5 because I've got a chlorine in there. Otherwise, I'm saying the cation has negative mass, which would be cool, don't get me wrong, but probably not gonna happen. So, if this is 42.5, and the chlorine itself is 35.5, so if I subtract 35, I get
7.05.
35.5, I get,
7.
It's like,
which leaves me with
LIs,
lithium chloride,
liquid.
okay? So that's kind of a cool way, so this way, you don't have to know the molar mass of everything, but, so on a situation like this, if I can figure out what the moles of one of them is, on that mole ratio, I can figure out what the other ones are, okay? All right, so we're cool with that. Let's talk, you want to form a precipitate. What's the relationship between QSP and KSP? Which one's going to be bigger? If you want to make a precipitate.
KSP.
K is small though, so Q is bigger.
Okay, because remember, when you look at a KSP calculation, right? Anytime you see big K, let's talk about this. Let's say it's silver chloride. Okay, speaking of which, so you've got the KSP of silver chloride, right? So if this is going to be a 1-to-1 ratio, this is going to be X and this is going to be X, right? Because Mother Nature wants to be in equilibrium, and when Mother Nature is not in equilibrium, Mother Nature flips out, okay? So remember, your QSP is calculated right after everything has been mixed, okay? This is going to be important. So let's say, for example, you've got, I don't know, a 0.2 molar solution of XCl, and you've got, I don't know, 20 milliliters of that, okay? And then you're going to have a 0.1 molar solution of silver nitrate, and you've also got 20 milliliters of that, okay? And you're going to mix these two together. Now, remember, you're going to be talking about the formation of silver chloride. So that's going to be ionized into Ag and Cl. So your KSP would be your silver ion concentration times your chloride ion concentration. Everybody cool with that? So remember, when you calculate QSP, QSP is like a snapshot. It's going to tell you which direction this thing is going to go. So what do I need to calculate QSP? Do I need the molarities before they're mixed or the molarities after they are mixed?
after you divide by the total volume,
Huh?
you divide by the total volume, right?
Yeah.
So after.
Yeah, because you have the concentrations before they're mixed, which do you any good, okay? You have to have the concentrations after they are mixed, okay? That's going to be the whole key to this. It has to be the concentrations after they are mixed. Now, conveniently, look at this. I got 20 milliliters and I got 20 milliliters. So what am I doing with the volume?
Doubling.
I'm going to double the volume, so what's going to happen to the concentrations? They're going to be half as much, okay? It would be like I'm going to take all of you, but I'm going to put you in a room twice as big, okay? Your concentration is going to be half as much. I'm still going to have the same number of you, okay? But you're going to be in twice the volume. So my QSP calculation would be 0.1, which would be my silver ion concentration, right? Because it's going to be half of 0.2. And then I've got a chloride ion concentration, which is going to be half of 0.1, which is going to be 0.05. Okay? So somebody take 0.1 times 0.05, and you should get 5 times 10 to the negative third.
Yeah.
Okay? So, if you look at the KSP of silver chloride, the KSP of silver chloride is I don't know, I wanna say it's something like 10 to the negative eighth. Okay, I'm just making up a number, it's 10 to the negative eighth, let's just say. So since my QSP is so much bigger than my KSP, what's gonna happen?
It will precipitate.
It will or won't? It will, because Mother Nature wants to get that QSP equal to the KSP. So Mother Nature's gonna sit there and go, whoa, 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 whoa. We got way too many ions in this solution. Some of you are gonna have to form a precipitate because I can't handle the situation as it is now. Okay? You guys remember, and this is important, just because you form a precipitate doesn't mean that the reaction didn't happen, that there aren't still ions in the solution, okay? There are still ions in the solution, but the concentration just puts it in equilibrium, okay? So get that out of your minds now. Oh, I formed a precipitate, there's no ions in the solution. No, there are ions in the solution, but it's just making it so that it's in equilibrium. Now, what if that KSP had worked out to be exactly equal to the QSP?
And it would be an equilibrium and there would be a precipitate.
Yeah, it would just, everybody's just chilled out, you know, there's no need to make a precipitate. If it had been less than, it certainly wouldn't have made a precipitate. So up here, whoops, come back here. So up here above, you've got some ions floating around, which in this case are going to be a few silver ions and a few chloride ions, okay? And you've got that precipitate floating down below, okay? Now, if I add some water to this, and there's still some precipitate that's observed, is the solution still in equilibrium? Yes. Because Mother Nature's sitting there and go, okay, hey, there's just more room. So I still want it to be in equilibrium. So I'm just going to take some of that precipitate and make it dissolve. Now, what if I added some silver ions into it? Maybe I add some silver nitrate back into it. What would happen to the amount of precipitate?
It would
Increase.
It would increase because Mother Nature is going to sit there and go, whoa, 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 you're adding more ions. I can't handle this. Okay? I got to make that precipitate come down. What do you know about the chloride ion? Is the conjugate base off of a weak acid or a strong acid?
Strong acid.
It's a strong acid. So if I added nitric acid to it, would that do anything?
No.
No, because the chloride ions aren't going to bond with the hydronium ions. They're going to be like, hey, whatever. Now, if instead of chloride, let's say it had been the conjugate base off of a weak acid, okay? Let's say it had been NO2 instead of NO3. Let's say it had been NO2. If I add a strong acid to that, then what's going to happen?
Then it would pull more stuff out of solution.
Why?
Because there's more hydronium ions, so it'll form. Huh?
Since it's
Keep going.
Yeah, there's more hydronium ions. So that means those would form.
So when you
bonds.
add those hydronium ions, what are you going to form?
HNO2.
Yeah, you're going to form nitrous acid, HNO2. So what's going to happen to the concentration of the NO2 ions in the solution?
It's going to go down.
It's going to go down. Mother Nature flips out and says, hey,
We need to add some more.
we need to make some more precipitate to balance that out. Okay?
Make some more? Or
Excuse me,
release?
dissolve more precipitate to maintain that equilibrium up above. Let me see. Let's say that you have a pH volume curve.
Ooh.
And let's say this is some weak acid. Okay? And what are you going to call that point right there?
One equivalence point, or half equivalence point.
Equal.
Is it, there's a big difference. Is it the equivalence point or half the equivalence point?
Equivalence
It's the EQ
point.
point.
That's your equivalence point. Now, assuming that you are in a 1-to-1 ratio, okay? So this would be some acid reacting with hydroxide,
Our favorite equation.
making water and the anion, okay? Right? So allowing for the fact that this happens, what could you use to find?
M1
V1 equals.
Now you could use M1 V1 equals
M2, V2, and then multiply and or divide by.
by 5. Exactly. whatever. Okay, because remember, that's the only time you can do that is when everything is in a 1-to-1 ratio. Multiply by 5, divide by 5.
Yeah. Just multiply each side by 5 and then divide each side by 5.
And then take the square root.
And then take the square root, but then square it.
Yeah. Okay. So, now, if this is a weak acid, is that equivalence point going to be at or above 7 if you're titrating it as a weak acid? Above 7, why?
Weak acids start with a higher pH.
Well, no, that is true, but that isn't why.
Double reaction.
Because if it's neutralized, what's going to happen over here on the right side? The anion is going to react with the water. So this is where you get that secondary reaction with the water, and you're going to get
The acid plus hydroxide.
plus hydroxide because you're going to be generating some hydroxide ions, therefore the pH is going to be above 7. Okay? Now, let's say it had been a strong acid and a strong base. Like let's say, for example, hydrochloric acid and sodium hydroxide. And you neutralize it. Then what's the pH going to be?
7.
Because over here, you're going to get water, you're going to get sodium chloride. But neither the sodium nor the chloride are going to alter and react with those water molecules. Okay? So, when you neutralize a strong acid, strong base, we're not saying that a reaction didn't take place. You are making salt water. Okay? But neither the sodium nor the chlorine is going to alter the number of hydronium ions or the hydroxide ions. Okay. Now, what do you call this point?
Half equivalent.
That's your half equivalence point. At that point, what does your pH equal?
Your pKa.
Your pKa, because if you go to the Henderson-Hasselbalch equation, that pH equals pKa plus the log of your anion divided by the concentration of your acid. Okay? So, prior to this point, okay? Prior to this point, what do you have more of? The molecular form of the acid or the anion?
Acid.
That's right, because you're starting, it's HA plus your hydroxide. So as the reaction goes, what happens to the concentration of your HA?
Increases.
It decreases because it's getting used up. What's going to happen to the concentration of your anions? They're going to increase. So prior to this point, you have a higher concentration of HA. After this point, you have a higher concentration of your anions. Okay? So at halfway through that, those two concentrations are the same. So that's why when you look at this Henderson-Hasselbalch equation, at your half equivalence point, these two values are the same. So you're taking the log of 1. Well, what's the log of 1?
0.
0. So this whole thing goes away. Your pH equals your pKa. Now, when you're trying to pick an acid to use in the preparation of a buffer, what do you know about your pKa relative to the pH that you want to end up with? Yeah, you can pick ones that are pretty close together. So if you want to prepare a buffered solution that's around 7, okay, you want to choose an acid that has a Ka of something around 10 to the negative 7. Because when you take the negative log of 1 times 10 to the negative 7, that gets you 7. Hey, so it's going to be something close to that. So don't pick an acid that has a Ka value of 1 times 10 to the negative 11. Okay? It's going to be a train wreck. Because then you're going to start off here at 11, and you got to drop that all the way down to 7. No. Okay? So always remember, if you're preparing a buffered solution, you always want to pick one that has the pH close to the pKa. Okay? Cool with that. Let's see what else. As the strength of an acid decreases, what happens to the strength of the conjugate base?
Increases.
It increases, right? Because Ka times Kb gets you
1 times e to the negative 14.
1 times 10 to the negative 14th. Otherwise, then don't tell me that's water. It is the
Ionization.
auto-ionization constant of water. okay?
Get into some. Those,
If you have a base reacting with water, what are you gonna get out of that?
Oh, jeez. Your the H3O
hydrox-
something.
Wait, HB plus OH minus.
Something like that.
HB, okay, this is a weak base, right?
Yeah.
Right? Pretty cool with that. It's a weak base to react with water, okay? So, do I have to give you the Kb value of that base?
Give us the Ka.
I could give you the Ka of the acid, and then you divide that and find the Kb. Now, so in this situation, your Kb is your Hb concentration, because it's always products over reactants divided by, right? So here's the kicker on this problem. When you find your X, what are you finding?
Your OH concentration.
Yes, you're finding your OH concentration, you are not finding your hydronium ion concentration. So what are you going to have to do?
Subtract your POH from 14.
Exactly, so once you find that, you're finding your POH, you get to subtract that from 14, boom, there's your KH value, or pH value. Okay, let me see. Quick review. What's the difference between the anode and the cathode?
Anode is where oxidation occurs, and cathode is where reduction occurs.
That's what
Reduction. So let's say that you want to build a galvanic cell or a voltaic cell, the same thing.
Wait, what? Oh, yeah.
And let's say that you have a strip of copper here and a 1 molar solution of copper nitrate. Okay? So I want to make some electricity. So I'm going to hook that up to something over here. So if I want to make this happen, and I do, the metal that I pick over here, is it going to be above copper or below copper on the reduction chart?
Below. No, above.
I want to make this reaction happen spontaneously, right?
You need something with a bigger reduction potential.
So over here, well, what's the reduction potential of copper?
0.34?
Yeah.
Really? Oh, wow.
I think, pretty sure.
Yeah.
That sounds right.
Right?
Silver is
Okay? So, what could somebody pick a metal over here
Silver.
that I can make this so that I get a spontaneous reaction?
Silver.
Zinc.
Zinc.
Or silver.
Zinc.
Let's go,
Silver.
don't go with zinc, because zinc is also 2+. Give me something that's not 2+.
Silver.
Silver?
I guess.
Silver. I
So
say
Ag plus 1 electron gets you Ag. So what's the reduction? So reduction potential of copper is 0.34.
And
So
silver.
what's the reduction potential of silver?
0.8.
So which one's going to be more likely to go in that reaction as a reduction potential?
Silver.
Silver. So what are we going to do with the copper?
Gonna oxidize them.
It's going to get reversed, so it's going to get
Oxidize.
oxidized. So this is going to be negative 0.34 plus 0.8, which is going to get you
A number.
44.
0.4. No, 46. 46.
0.46. My bad. I got wrapped up on the fours.
Wait, 46? 46?
4.6, yeah.
Well,
I don't know how. Yeah,
Okay.
46. Yeah.
So is the reaction going to be spontaneous?
Heck yeah.
Yes. Is delta G going to be a positive or negative number?
Negative.
Actually, there's no salt bridge.
Oh, yeah, you're right.
Hey,
It was a
look at
trick
salt
question.
bridge.
Yeah, salt bridge.
Which direction do the electrons flow through the salt bridge?
Well, there wasn't any originally, so.
Wait, what?
It's a trick question.
They don't.
Yeah,
They go through the
electrons-
electric
Electrons
current.
don't flow through the
Oh.
salt bridge. Electrons flow through the external circuit. Okay. So the Ag plus, that's going to be the reduction. So is this side over here with the silver, the anode or the cathode?
Cathode.
That's going to be my cathode. Okay. So then which direction are my anions gonna flow? From the
Towards
anode
the
to the
cathode.
cathode, or the cathode to the anode?
Towards the cathode.
So my electrons are gonna be flowing from the copper over to the silver. So what's gonna happen to the mass of the copper over a period of time?
Decrease.
It's gonna decrease because you're gonna turn them into
Copper ions.
copper ions. The silver side is going to
Increase.
increase in mass, okay? Because you're gonna be making more silver. So what's the overall balanced equation?
Eg2 plus, or 2Ag plus
Cu2 plus.
Cu
I can't have plus
Cu plus
Cu2 plus.
plus Cu
Cu with
Oh, yeah.
Cu2 plus.
2Ag
Cu2 plus
2
2Ag.
2 Ags.
2 rad.
That was chaos.
Okay? So if you were to use the Nernst equation, E equals E naught minus 0.0592,
Yeah, that looks familiar.
what's N gonna be?
2.
2. Now, am I gonna have my copper ion over my silver ion, or my silver over my copper?
Copper over your silver, products over reactants.
Products over reactants, but what's gonna happen to my silver ion concentration?
It's gonna
It's going to get
squared.
squared, okay? Now, let's say we start under standard conditions. Under standard conditions, what is the molarity of each?
Why?
1.
1, okay? Under standard conditions, the molarity is 1.
Didn't know that.
Over a period of time, what's gonna happen to my copper ion concentration?
It's gonna go down.
Oh, decrease.
Oh, it's
Well,
gonna
you're-
go up.
It's gonna
No,
go
it's
up.
not. It's gonna.
No,
It's gonna go up because there's
What's
gonna
gonna
be.
happen to the concentration of my copper ion?
It's gonna go up.
It's
Gonna go up. What's gonna happen to the concentration of my silver
It's
ion?
gonna go down.
It's gonna go down. Look, the silver ions are turning into silver, the copper is turning into copper ions. So over a period of time, what's gonna happen to this value of Q? Will it go above 1 or will it go less than 1? Just the Q value. So
Just
the
the
copper
Q?
ion concentration is gonna be doing what?
Increasing.
Increasing. The silver ion concentration is going to be,
Decreasing.
So it'll be greater than 1.
so the Q value itself will be bigger than 1. So when I subtract, since this is going to be bigger than 1, am I going to be subtracting a positive value or a negative value?
Positive
So
value.
therefore,
Your total E will go
E
down.
is going to become,
Eventually zero.
Smaller.
yeah, eventually it'll go to 0. At that point, the cell has no, gives free energy because there's no potential for anything to move. Okay? Okay, so we got that. Now, let's say over here, where I've got like the silver nitrate, let's say that I add some hydrochloric acid over there. Okay?
Zesty.
I dump some hydrochloric acid in with the silver nitrate. What's gonna happen? What's gonna happen to the concentration of silver ions?
Go down.
Why, Anna?
Because it'll form a precipitate with the AgCl.
Yeah, because HEC